we are going to look at our water chapter. In this chapter, we are going to look at hardness in water, water treatment, water pollution, sewage treatment, and water analysis, and the various subheadings under all of those. The first one that we're going to look at in this particular video is hardness in water. So, definition of hardness in water. Hard water is water that does not form a lather easily with soap. As we know, water is a great solvent, and the main cause of your hardness in water is this very property, the fact that it's a great solvent. So as it flows over the ground, it will dissolve some of the minerals from the rocks, and the particular ones that cause hardness are calcium ions and magnesium ions. How do they cause hardness then? Well, when hard water reacts with soap, the sodium stearate in the soap reacts with the calcium 2+ ions or the magnesium 2+ ions, and that's what forms a scum. Now, the scum really is a kind of a greyish precipitate of insoluble calcium stearate. Here's our equation. So you see your calcium 2+ ions there, and the more observant among you will remember that stearate ion there from when we did our saponification. And then the stearate ion is bonding with the calcium, and that's forming calcium stearate, which is your insoluble precipitate, or as we call it, soap scum. Of course, that wastes a lot of soap, but we'll come to the advantages and disadvantages of hardness a bit later. So that's an overall summary of what hardness is. Now let's look at the different types of hardness that you can get. So the first one is temporary hardness. Now, as the name suggests, temporary hardness is hardness that can be removed, and the main method of removing it is by boiling. It's generally caused by the presence of calcium hydrogen carbonate. Now, where does this calcium hydrogen carbonate come from? Well, if we go back to what we said about water being a really good solvent, and we have a situation where we are producing lots of carbon dioxide in our world at the moment, and some of that carbon dioxide can get dissolved in your water. And if it reacts with that water, you get a weak solution of carbonic acid. I'm pretty sure you'd have covered this already in geography, if not junior science. Now, when that carbonic acid then flows over a limestone region in particular, it will react with the calcium carbonate. Calcium carbonate is not soluble in water, but it is soluble in carbonic acid, and it will form calcium hydrogen carbonate, or calcium bicarbonate as it is sometimes known. So effectively, you formed a very dilute solution there of calcium hydrogen carbonate, and that is your hard water. Now, how would we get rid of this hardness? Well, we've mentioned already at the top of this slide that you can get rid of it by boiling, and the next slide will show you what happens when we boil it. So the calcium hydrogen carbonate, when it's heated, forms a precipitate of calcium carbonate, and the carbon dioxide is released, and so is the water. So that leaves your water now without any calcium ions in it, so it is effectively soft water. But where does that calcium carbonate go? Well, it actually forms an insoluble scum around the heating element of the, say, kettle, if that's what you're using for boiling it, or it could be a water boiler, a water tanker, or heater, and it eventually builds up to look like a really bad limescale problem. We call that calcium carbonate limescale, and it has an overall effect of making the heating appliance have to work harder to heat the water, and so we tend to try to remove it. because if we remove that lime scale, we should be able to increase the efficiency of the kettle or the water heater or whatever we happen to be talking about there. So this equation up here could be thought of as the reverse, I suppose, of the process of forming hardness in water, because you're starting with your carbon dioxide and your water, and if you remember, they formed carbonic acid, and when that ran over calcium carbonate, it formed your calcium hydrogen carbonate, which was the dilute solution that we call hard water. So now when we're removing it, we're going backwards. We're starting with our calcium hydrogen carbonate over there, which is our hard water. And when we heat it, we are precipitating out the calcium carbonate as an insoluble white solid that forms the lime scale. And also then we're getting our carbon dioxide back and our water, not attached in any way to calcium ions anymore. So it is now soft water. Right. There's a second type of hardness, and if the first one is called temporary, it stands to reason that the second one would be called permanent hardness. And again, as the name suggests, this is hardness that cannot be removed by boiling. It's caused by the presence of different ions in this case. It's calcium and magnesium sulfate that cause your permanent hardness. Now, even though it's called permanent, it's not irremovable. Sorry, there are just some pictures of your hardness clogging up various different things. Okay, even though it's called permanent hardness, you can actually remove that hardness too. So here are some other methods in addition to the boiling that we mentioned earlier. Boiling can be used to remove temporary hardness, but the following methods can be used to remove all types of hardness, temporary or permanent. Distillation is one, addition of washing soda, which is common in bath salts, using an ion exchange resin, or using a deionizer. Now, the one that looks the simplest to us probably is distillation, in that we've come across it before. We know the principle of distillation. So you heat the liquid, in this case water, you boil it, and then you pass it down through a condenser and it comes out the other end, but it's left all of the impurities behind it. So what you get out at the end is distilled water, a very pure water. Now, the problem with this process of boiling the water and then condensing it is, yes, it removes all the dissolved solids and the liquids and the gases, but it is quite expensive, and therefore it's not really suitable on a large scale to be using distillation. And so there are some cheaper methods of removing hardness. One of those is washing soda. So washing soda is hydrated sodium carbonate. Here's the formula, Na2CO3 10H2O. And when you add that to the water along with your soap, it'll soften the water by removing the calcium ions. And here is the equation for that. So you have your calcium 2 plus, and it's reacting with sodium carbonate there to give you calcium carbonate as a precipitate, and then releasing the sodium. So those calcium ions there are being precipitated out of the solution as the insoluble calcium carbonate, and the sodium ions are staying in there dissolved in the water, but they've no effect on it. That sodium carbonate is used in particular in bath salts. So if you've had baths in Epsom salts, that's what you'll have used. Epsom salts are basically sodium carbonate with nice little perfumes added. Okay, then another method that you can use, so we've covered distillation and washing soda so far. Another method that you can use is an ion exchange resin. Again, there's a clue in the name. Ion exchange is what we're doing here. So we're going to take out our calcium ions and our magnesium ions, and we're going to replace them with another positive ion. So the resin is a synthetic material, and it swaps out the ions that cause hardness for ions that don't. Here's a cation exchange resin, um, it will swap out your calcium ions for sodium ions. Obviously, 2 sodiums for every 1 calcium. And then those calcium ions stay inside in the resin. If you look over here at the picture, you can see the setup. So when you pour in your hard water, it has calcium ions in it. It goes into this resin that has loads of potassium ions in it, or excuse me, sodium ions in it. And the sodium ions replace the calcium ions in the water, and the calcium ions stay in the resin and the sodium ions come out at the end. But of course, those sodium ions don't cause any wastage of soap. They don't contribute to hardness in the water. So that's your ion exchange resin. Now, that would be suitable if you were trying to get rid of hardness in a domestic setting, we'll say. I should also mention that that ion exchange resin, of course, would not last forever, because if you can see there, you're putting in some calcium ions into it. Eventually, you'll have replaced all of those sodiums with calcium ions, so it can be replenished by pouring a concentrated solution of sodium chloride through it. And that sodium chloride then will go through the resin, and the sodiums will replace all the calciums that are in there, and you'll be able to reuse it. But anyway, that's your ion exchange resin, which is good on a domestic setting for removing hardness out of water. But if you were working in a lab, you might want to get rid of all of the ions out of the water, not just these positive ions that are causing hardness. And if you wanted to do that, you would use a deionizer. Now, again, the clue's in the name, deionizer. So it's removing all of the ions, the pluses and the minuses. And it's doing that by having a mixture of two resins. It has a cation resin and it has an anion resin. The cation resin exchanges all those positive ions like your calcium and your magnesium for H pluses. So it puts H pluses into the water and takes out the calciums, the magnesiums, etc., any plus ions. Then the anion resin takes out any of the minus ions and it sticks in OH minus instead. Now I'm sure you will work out that if you have H pluses going into the water and you have OH minuses going into the water, the last thing that will happen is that they will bond with each other to form just more water. Now, that gives you a very pure product when you think about it. You've taken out all the plus ions, you've taken out all the minus ions, and you've replaced them with H pluses and OH minuses, which link up to form H2O. So what comes out at the end of your deionizer, having gone through those two resins, is water with no ions in it. But while it's very pure, of course, we will remember back to a question we did a good long time ago that was comparing deionized water with distilled water. And deionized, if you remember, is not quite as pure as distilled water, because in deionized, yes, you've got rid of all the ions, but you might not have got rid of other dissolved gases or dissolved solids or suspended solids that were not ionic in nature. So any of the covalent substances could still be left in the water. So that water is not quite as pure as your distilled water. That's probably the purest form you can get. Finally, so in this section, we're going to look at the pros and cons of hard water. And we've mentioned a couple of these as we've gone along. So the advantages of hard water. Well, if it has calcium ions in it, that's going to be good for our teeth and our bones, for maintaining the strength of teeth and bones. It also gives it a much nicer taste. There's a really nice taste to water with a bit of calcium in it. And because of that nicer taste, this water is more suitable for brewing. It's also more suitable as it happens, for tanning leather. Then the disadvantages. Obviously enough, if the calcium becomes deposited on heating pipes, it's going to block them. It also leaves lime scale on the heating element of your kettle or any other appliances that are heating water. It wastes soap, we mentioned that already, and it produces a scum around your bath and your sink that you have to clean up. So those are the pros and cons of your hard water. We leave it there for now. The next section that we're going to look at will be water treatment. I'll do another little video on that.